Welcome back. Today, we're going to be looking at simple harmonic motion. So we're going to be taking a look at our Hooke's law that we had from before and the potential energy stored in here. And we'll talk about what happens if now, instead of being in equilibrium, we put this in motion. Okay, so let's get started. So it turns out that many of the motions that we see take the form of simple harmonic motion. And let me give you an example. If I put this mass on here, and I pull it down and I let it sit, this is in equilibrium. I'm going to take this one off. This is currently in equilibrium. So the force that's exerted down on it, force due to gravity on this mass, is compensated by the force of the spring pulling it back up. But if I pull it down a little bit more, what I've done is I put in more force down. So the force of the spring has to be greater as well. So that when I release it, this thing now begins to vibrate. And I'm going to draw that up really quick. So if I have this as my hanging mass, and it's got that mass, it's sitting on there. This is in equilibrium at this point right here. So the force due to gravity that's pulling down is exactly equal to the force of the spring pulling it back up because it's in equilibrium. But if I stretch it further down, so down to here, oops, hang on, let me do a better spring on that one. So I bring this down and then I do my spring and I stretch it down here. So now it's pulled down this far. So you can almost say that this is my change in my spring length right there. What ends up happening is that now my force down is bigger. It's my force due to gravity plus what I put in. So my force on my spring must also be bigger. So that when I release, this thing is going to accelerate up. And so I'm end up having, when I release it, I'll end up having a net force up in this instance. If I look at when it goes all the way up then, it compresses. Now here's my mass. My force due to gravity is back to being normal. It's what it was before. But now because it's compressed, my force of the spring is less than the force due to gravity. So I end up having a net force is down. But in each case, if I extend this equilibrium line out, because it's the same spring, you'll notice that in each case, my net force is pointed towards the equilibrium line. And so when it does that, my force is always being pulled towards the center. It's very, very similar to when we talked about circular motion. And this force, actually, this force is very similar to centripetal acceleration or centripetal force. Now, why is this important? Because what happens is that you notice this thing's been going up and down for a while. This simple harmonic motion is a motion that regularly repeats itself. So as it goes up and down, the time it takes for it to go up and down and up and down and up and down is the same each and every time. That's what makes it. It's a motion that will regularly repeat. It's the same every single time it goes through that motion. And this is important because it's going to jump us into waves. Okay? But before we get into the other types of simple harmonic motion, we need to define a couple of definitions. The first is amplitude. And amplitude by definition is the maximum amount of displacement. From equilibrium. That's going to be measured in meters. And so when this thing goes down, initially, remember, we had it started, and I'm going to stop this for a second, but initially, when it was in equilibrium, it sat right at that height, right where my fingers are. Okay, if I pull it down, that's how far it's been displaced. When it vibrates, it's going to go the same amount down as it does up. And it's going to continue to go back and forth and back and forth and back and forth. And the maximum amount displaced, that's what's called amplitude. The period is the time it takes for one vibration. Or oscillation. You'll hear me say oscillation sometimes too. I'll put that in parentheses. Now, it's time. It's simple as a capital T, but it's not just any time. It is a time that it takes to go up and down once through one vibration. So if it starts at the bottom, so there's 1 and 2 and 3 and 4. It's an up and down. The whole thing has got to be one vibration or one oscillation. It's going to be measured in seconds. It's still time, but it's a perfect time of going up and down and up and down and up and down. Okay, and remember, simple harmonic motion, this time is the same every time. And again, it's been going for a while. It's going to continue to go for the length of this video. And eventually, if there wasn't friction, would still be going when you guys walked in here tomorrow. Frequency, on the other hand, is the inverse of period. Frequency is defined as the number of vibrations or oscillations that occur in 1 second. And so frequency is the inverse of period. And I'm going to put that in red. We can say that period is 1 over the frequency, or frequency is 1 over the period. They're inversely related to each other. And as such, then, my units of frequency are 1 over seconds. Or you'll sometimes see it as seconds to the -1. That's sometimes how it's written out. But more commonly, it's known as a hertz. HZ. That's a Z. I know it doesn't look like a Z. We'll try that again. Hang on, I gotta go back to this sharing screen. Share screen, there it is, share. HZ. Beautiful. Okay. Now, the two cases of simple harmonic motion we're going to look at, you're looking at one of them. This is a vibrating mass on a spring. Okay. And as you can have plainly witnessed, this thing regularly repeats itself. And it's going to go on until it loses all of its energy to friction. So that's a vibrating mass on a spring. The period can be found. The amount of time it takes for it to go up and down can be found through the formula T, and I'll put mass on spring, is equal to 2 pi times the square root of the mass over the spring constant. Okay. Now, you will not find this formula in your reference table. Anytime I want you to do something like this, and we're going to do something like this in a lab, okay? But anytime I want you to do this on a quiz, I will give you this formula. I have to, okay? But what you're talking about is T is the period, the time it takes for it to go. M is the mass. And so we're saying if you increase the mass, you should increase the period. And I can show you that to you really quick. So if I attach this on here and send it up and down, you can hopefully plainly see that that's taking more time to go up and down than the other one did. And K is the spring constant, which should make sense too, because if you have a larger spring constant, you're going to have more force trying to pull it back to that equilibrium point, and therefore the acceleration is going to be greater, and you'll be going quicker. So the period will be less. The other type of simple harmonic motion we're going to look at is the pendulum. Okay, and the best example I've got, I usually bring this out, my keys. And that goes back and forth, and back and forth, and back and forth. And it's a motion that will regularly repeat itself. You can see this in grandfather clocks. Some cuckoo clocks have this. Okay? And it turns out that it is so regular that you can use this. They use this for clocks to make sure they time out the amount of time accurately. Okay? And initially when they built these, the Swiss built the clocks, they built these via pendulums, so that you could accurately count the amount number of seconds in a minute, so on and so forth, and the time would be right. Now, if I were to draw this out, here is my pendulum at different spots. Again, down at the bottom, here's my equilibrium. point. When I pull this off to the side, my force due to gravity is going to be pulling that pendulum back in. By the way, just for reference, this pendulum name is Bob. I don't know why they call it Bob. That's just the name. The thing in the mass in the bottom, it's called Bob. So if I pull Bob off to the right-hand side, there's a force pulling it back down to the equilibrium. As it swings through, that force of gravity shifts and tries to pull it back towards that center again. It's gravity that's trying to get down to that lowest point again. And so this is a motion that when you set it free, will swing back and forth and regularly repeat itself as well. But again, notice one thing, the force is pointed towards the center. It's showing that it's similar to that centripetal motion, that centripetal acceleration and centripetal force we talked about before. Everything's trying to get back to the center. Now, period-wise, the formula for finding the period, again, you won't find this one in your reference table either. I will give it to you. But to find the period of a pendulum is going to be equal to 2 pi times the square root of L over G. And that's because it's the force due to gravity, acceleration due to gravity, that's acting on it to try and get it back to that middle. But it's also going to depend upon the length. And I can show you that really quick. If I go this back and forth and back and forth, if I make it shorter, it goes back, forth, back, forth, back, forth. Okay? And so we'll talk about this. I'll give you an example tomorrow about how the Swiss, when they made these clocks, would adjust these to make the period just right. And it's also a way that we can determine what the acceleration due to gravity is. We'll try and do that in a lab. Okay, so we're going to call it quits for today. Tomorrow we will start with waves and make the jump from simple harmonic motion into waves and start our major topic. So everybody have a great day. We'll see you later. Bye.